Hello students. We have been dealing with Laplace transforms, inverse Laplace transforms, first shifting theorem, second shifting theorem, unit step functions, how to convert a step function into a combination of unit step functions, how to solve differential equations with initial conditions given using Laplace transforms, and such questions we have been dealing with. So in the next session, we will start with short impulses, and we will be dealing with a concept, a function called Dirac delta function. And then, as we move on forward, you can see how Laplace transforms will affect differentiation, integration, and how it behaves with each other. So let's start today's session with what is a short impulse and how can we move forward with it. Okay. In our daily life, we tend to see many kind of forces. There are some forces which act at just an instant. For example, suppose if a cricket ball is being hit by the bat, and the force at that instant is very large, but it just acts at that instant. Like that, suppose if a hammer is being hit on a system or on a table, so there is a force acting at just that instant. Similarly, if a gun is being shot, there's huge force acting just at an instant. So these are all some examples of such forces which are large. The forces are large, but the time they are having to act is very less, instantaneous. So this is a small session which deals with such forces. Before moving on, just let's see what is an impulse of a force. Suppose you're given a force f of t, and this force f of t is acting in the period a to a plus k. Suppose if it is given, then the impulse of this force is defined as the integral from a to a plus k f of t dt. So that is called the impulse. Suppose if this k is tending to 0, that means a plus k is tending to a. That just means that the time interval in which the force is acting is very, very less. So that is a possibility of a kind of force which we just mentioned before. The force, the acting of the force is just for an instant. So that you can see that as a remark. Suppose k tends to 0, that means the force is acting only for an instant. And the next concept we have to introduce is unit impulse function. So before introducing that, we have to define a function which is denoted by fk of t minus a, where this k and a has definite they are denoted here because they are involved in the function. Okay, this function is having the value 1 by k when t varies from a to a plus k, and on all other places the value of the function will be 0. That is the function f suffix k of t minus a. So this a and k has definite places in this function. See, a is the the interval from which the time starts, a to a plus k, and this k also happens to be the value here 1 by k. Okay, so the next aim is to find the impulse of this function, the new defined function. The new defined function is fk of t minus a, and we are going to find the impulse. Suppose call that impulse ik. The impulse of this function is ik. Okay. The impulse will be from a to a plus k, the integral from a to a plus k fk of t minus a dt. Right? So from a to a plus k, why we are writing this? Because even if the function is from a to infinity, if we are splitting it, or it, even if it is from 0 to infinity or from minus infinity to infinity, in every other place the value of the function is 0. So we just have to consider the interval from a to a plus k. So the function will be having in this interval the value 1 by k. You substitute that, and when you evaluate, you have 1 by k is a constant. Then we integrate dt, that becomes t, and t is varying from a to a plus k. Then a plus k minus a, when it cancels out, you get 1 by k into k is equal to 1. So impulse of this particular function we define now is 1. Okay. So the next question is, so when you saw this function, you can see that it acts like a step, right? And the height of the step is nothing but 1 by k. 1 by k is a constant here. So it is like a step. So the next question is, convert this step function into in terms of unit step functions, and then find its Laplace transform. This is our next aim. So you are given fk of t minus a. We know how we generalized the combinations, right? So you have to multiply this 1 by k with u of t minus a minus u of t minus of a plus k, okay, plus 0 into every other areas, right? So you have fk of t minus a to be written in terms of unit step functions as like this. Okay. Now what you have to find, what is it we have to find? We have to find the Laplace transform. Okay, so Laplace transform of fk of t minus a is equal to Laplace transform of this combination. And using linearity, you can take this 1 by k out and then split both of them, right? And you know that the Laplace transform of u of t minus a will be e raised to minus a is divided by s minus Laplace transform of u of t minus of a plus k will be e raised to minus of a plus k into s divided by s. And this s can be taken out. So what remains is these, right? And e raised to minus as can be taken out. So what you obtain is e raised to minus as divided by ks into 1 minus e raised to minus ks. That is the Laplace transform of fk of t minus a. Okay. Now we are going to define the function called unit impulse function. The unit impulse function is nothing but the Dirac delta function. You can call them any of these names, Dirac delta function or unit impulse function. This function is nothing but limit k tends to 0 fk of t minus a, and we denote it as delta of t minus a. Okay, so to understand this function, we are drawing in the remark, you can see a graph. Okay, this graph says that from a to a plus k, the functional value is 1 by k. See? And in rest of the other places, the functional value is 0. So this is what fk of t minus is. And now what did our Dirac delta function says? We have to tend this k to 0. Then only that will become Dirac delta function. So what will happen? This, when k is tending to 0, this interval become, this a plus k will become very, very close to a. That is, a plus k is approaching a. See, both are becoming together. And this 1 by k, what happens to this 1 by k? When k tends to 0, 1 by k will tend to a very large number, or we usually denote it as infinity, the infinite value. So this 1 by k at this point a, the value will be going like, we cannot just even measure. It will be going like this, up, moving to infinity. So that is how the Dirac delta function appears when we are drawing. Okay. So we have to note that for the Dirac delta function delta of t minus a at the time a has infinite value for the corresponding uh, coordinate, y coordinate. And suppose if the Dirac delta function is a force, the corresponding force at that instant will be of infinite value. This was thing we first discussed when we said that an enormous large force is acting at an instant. So that force can be uh, made equivalently thought to be this Dirac delta function. So this Dirac delta function is also called the unit impulse function. So our next question is to find the Laplace transform of Dirac delta function. So for that, Laplace transform of delta of t minus a is equal to Laplace transform of limit k tends to 0 fk of t minus a, right? So we are assuming that the limit and the Laplace transform can be interchanged here, and every hypothesis of such an interchange is satisfied. Okay, and this limit is taken out. Hmm, and we are trying to find the Laplace transform here, right? So we had already found out the Laplace transform of fk of t minus a. So you are just giving the value of that here because we had already found it out. Okay, and then we are asked to let the limit k tends to 0. So when k is tending to 0, something happens here, right? If k is tending to 0, this value becomes 1 and the top portion will go to 0, and if k is tending to 0, the denominator portion also goes to 0. That means this value will be of the form 0 by 0, and then we can apply the L'Hopital's rule. Okay, L'Hopital's rule, for applying L'Hopital's rule. Before that, what we are going to do is we are just taking out terms which doesn't involve k. Okay, so we can see that in the numerator e raised to minus as doesn't have any relation to k. There is no presence of k, and s also doesn't have any presence. So we are taking out e raised to minus as divided by s, and then thinking about limit k tends to 0, 1 minus e raised to minus ks by k. That is also in a 0 by 0 form as earlier. So we are applying a L'Hopital's rule. L'Hopital's rule says that if such a thing happens, uh, we can take the limit k tends to 0 and find the derivative of the numerator divided by the derivative of the denominator with respect to the variable which is tending to 0, or the in the limits, variable in the limits. So here we have the variable to be k, so we should take the derivative with respect to k. So d by dk of 1 minus e raised to minus k is divided by d by dk of k. Okay, and when we take the derivatives, you get this 1 will be getting giving you 0 minus e raised to minus ks into, we are taking the derivative with respect to k. So we will get minus s here, right? Divided by 1. So that means e raised to minus as divided by s into limit k tends to 0, s into e raised to minus ks. And this portion goes to 1 because e raised to 0 is 1, and we have an s here and s here, and they cancel out, and at the end we get e raised to minus as. So what we got is the Laplace transform of Dirac delta function is nothing but e raised to minus as, which is a very important result. So you can see in this page that it is tabled out. It is an important result which we just found out. So thus we are giving a remark, delta of t minus a can be functionally written as at t is equal to a, the value will be infinity, and at every other point the value will be 0. Now we are going to find out integral 0 to infinity delta of t minus a dt. Okay, so integral 0 to infinity limit k tends to 0 fk of t minus a dt, right? And we are assuming that it is interchangeable, the limits and the integral are interchangeable, and Here we are assuming this a is a is greater than or equal to 0 since it's time, because a means a is less than or equal to t less than or equal to a plus k, right? So a is a definite positive quantity. Okay, so we are assuming like that. Okay, limit k tends to 0. What we are going to do next is we'll just split this integral from 0 to infinity into 3. Here we are making one integral go from 0 to a, the second integral go from 0 from a to a plus k, the third integral to go from a plus k to infinity. Okay. So we know that from a to 0 to a, fk of t minus a will be having the value 0. From a to a plus k, that will be having the value 1 by k. From a plus k to infinity, the value will be 0. So this becomes 0 and this becomes 0 and we are left with this. Okay. And then we are taking the integral to obtain limit k tends to 0, 1 by k t varying from a to a plus k minus a, and k cancels out and that becomes a 1, and limit k tends to 0, 1 is 1. So what we just found out is integral from 0 to infinity delta of t minus a dt is 1. So this is a kind of weird situation because we saw that at one particular point this Dirac delta function is having the value infinity at one particular point and the rest other points it's 0. But still this value which takes infinity at one point, when integrated from 0 to infinity, we are getting a finite value 1. So that is a kind of curious fact. So from the above remark, we can see that though delta of t minus a takes an infinite value, the integral is usually actually the area under the graph. The area under the graph is nothing but a finite value 1, which is strange. So delta of t minus a is not just a function in ordinary sense, because in ordinary sense, if a function takes the value infinity, the area will become infinite. But this is not a kind of normal function. So this function is we can better call it a generalized version of function. Generalized function. Okay, that is about the Dirac delta function. Now we are going to solve a question which is nothing but a differential equation having the initial conditions. So you're given this and you are asked to find and solve in two conditions. You're given an r of t and r of t is given two cases and you have to solve 1 and 2. Okay, so we are first going to solve 1. In the first r of t we are given u of t minus 1 minus u of t minus 2. It is already given in the form of unit step function, so we don't have to there is no necessity to convert into the unit step functions. So what you have to first do is apply Laplace transform on the given differential equation. I'm just applying, and we have to substitute for L of y double dash, L of y dash, L of y, and then substitute for L of u of t minus 1, L of u of t minus 2, and so on, and give the values of the initial conditions. Y of 0 is equal to 0, y dash of 0 equal to 0, substitute everything, and then make the y of s together, every term with y of s together, then combine them in braces into y of s, that is equal to the value on the right, and find y of s. Okay, so now y of s is obtained like this, and we saw that this is a quadratic form. We get plus 2, the sum is plus 2, the product is plus 2, the sum is plus 3, so plus 2 and plus 1 will uh, act for the factorization. So you can write the quadratic form here as s plus 1 into s plus 2, and you already have an s in the denominator already. So this is a case. Okay, so for our e sinus, we are going to do something. E raised to minus s minus e raised to minus 2s is kept in the braces as such, and the rest of the portion 1 by s into s plus 1 is being denoted as f of s. Okay, right? So this becomes is equal to f of s into e raised to minus s minus f of s into e raised to minus 2s. Okay. So this y of t, this is what we have to find. When we solve for a differential equation in y, y double dash and all, we are going to find y of t. So y of t is nothing but L inverse of y of s. Okay. That is equal to L inverse of f of s into e raised to minus s minus f of s into e raised to minus 2s. Apply the linearity of L inverse, you're getting this. Okay. Now what we are going to do is we are considering this f of s, and you can see that this is a very simple question in order to convert to mixed fractions s plus 1 s plus 2. So you have to write it just as a by s plus b by s plus 1 plus c by s plus 2. We are assuming it's so, and equating, taking the LCM and equating the numerators, you're getting like this. Okay. So when s is equal to 0, you get a is equal to 1 by 2. When s is equal to minus 1, you're getting b is equal to minus 1. When s is equal to minus 2, you get c is equal to 1 by 2. These are all very simple things you were dealing in class when we are doing these kind of problems. So now you have the f of s. You obtained a, b and c. You're substituting them. And then we are going to find the L inverse of this f of s. Okay. So, and you're calling that as f of t, like we do in the normal procedure. L inverse of 1 by 2 by s and minus 1 by s plus 1 plus 1 by 2 divided by s plus 2, and you're using the linearity, and then you get L inverse of 1 by s is equal to 1. L inverse of 1 by s plus 1 is equal to e raised to minus t. L inverse of 1 by s plus 2 is equal to e raised to minus 2t. Okay, and then the combination. This is what you got. So what you need to obtain is y of t is equal to L inverse of f of s into e raised to minus s minus L inverse of f of s into e raised to minus 2s, right? So this is in the form of the second shifting theorem, the corollary, which says that this is equal to f of t minus 1, because here the a is 1, here the a is 2. Okay, here it will be f of t minus 1 into u of t minus 1. Here it will be f of t minus 2 into u of t minus 2. And here the small f of t is nothing but L inverse of capital F of s, which we have found out here. Here also the same, because it's same function. Okay, so substitute for the values. Okay, f of t minus 1. So you have to replace this t with t minus 1 wherever there is a t, and here wherever there is a t you have to replace by t minus 2. Okay, and the next portion says about splitting, how to split the uh, intervals. So you can see that here there is a u of t minus 1, here there is a u of t minus 2. So u of t minus 1 will give us 0 to 1, 1 to infinity. U of t minus 2 says 0 to 2, 2 to infinity. So when we combine both of them together to justify, what you have to do, you have to first consider the subinterval 0 to 1, then you have to consider the subinterval 1 to 2, then you have to consider the subinterval 2 to infinity. So this is the way they have been given into subintervals 0 to 1, 1 to 2, t to 2 to infinity, right? And when you're considering 0 to 1, okay, okay, when we are considering 0 to 1, we know that the value of u of t minus 1 here will be 0, right? And u of t minus 2 will be also 0. Up till 1 here we have 0, up to 2 here we have 0. So up till, in common, when we are thinking about a common interval, that will be 0. So here and here 0. So in this portion value will be 0. Then 1 to 2. When we are considering about 1 to 2, we know that u of t minus 1 there will be, u of t minus 1 there will be 1, right? So this term will be there. Now from 1 to 2, u of t minus 2 will be 0, right? Because In this section we have, yes, from 2 only you are having the value 1. So you will get this value into 1 minus this value into 0. So that happens to be just this value. Okay. And then in the next case, you have 1 here and 1 here. So you have to add them all. When you add them all, I think this 1 by, yes, this 1 by 2 and 1 by 2 cancels out, and the rest of the terms will be there as the answer. So this is the answer for that. Okay. So now you have to answer the next one. Okay. Here we have the same differential equation on the left, and the right r of t changes to Dirac delta function at 1, delta of t minus 1. This means that at 1 the function has infinite value. Okay. So you have already calculated what the Laplace transform of delta of t minus a is. If it was e raised to minus as, here the a is 1. So you have L of delta of t minus 1 to be e raised to minus s. And here the usual. We have already calculated in the earlier, uh, the same question in the left, what is y of s and all. So you can just write them out. And here you get y of s is equal to e raised to minus s divided by s square plus 3s plus 2, where this can be split up into two factors, s plus 1 into s plus 2. And think about the 1 by s plus 1 into s plus 2 as an f of s. Okay. And now we are thinking about this f of s and making them into partial fractions, the sum of partial fractions, and it is easy to find out what is a and b. So when we are taking the LCM and equating the numerators, you get a into s plus 2 plus b into s plus 1 is equal to 1. When s is equal to minus 1, you get a is equal to 1. When s is equal to minus 2, you get b is equal to minus 1. Substitute a and b in f of s. So the small f of t will be L inverse of capital F of s, which will be equal to L inverse of 1 by s plus 1 minus 1 by s plus 2. 1 by s plus 1 will have the L inverse to be e raised to minus t. Here it will be e raised to minus 2t, and that is what we got for f of t. Now what is to be found is small y of t. Small y of t is equal to L inverse of y of s. Y of s was nothing but f of s into e raised to minus s. So you can use a second shifting theorem, the corollary, which says that here we have a to be 1. Uh, this will be equal to f of t minus 1 into u of t minus 1. Here the f of t had been already calculated. So f of t minus 1 is nothing but replace t minus 1 for t. So here we have e raised to minus t minus 1 minus e raised to minus 2 into t minus 1, the whole into u of t minus 1. Okay. And then you can write it out as a function. Here we are just dealing with u of t minus 1. So you can split up the interval as 0 to 1 and then 1 to infinity. 0 to strictly less than, t strictly less than 1, t strictly greater than 1. And in this section, we know that the value of the function will be u. The will be having function 0. So the value here into 0 will be 0. And in the other part, from 1 to infinity, the u of t minus 1 function will be having the value 1. So the value will be e raised to minus t minus 1 minus e raised to minus 2 into t minus 1. And that's the answer for the question. So the next question is y double dash plus 2 into y dash plus 2y is equal to delta into t minus pi. Y of 0 is equal to 1, y dash of 0 equal to 0. You have to solve this. This is also a very easy question. So in the first part, what you're going to do is take the RHS and you're going to find the Laplace transform of the RHS. Here we are just going for a change, we are doing like that. But we know it, so we have no we have an easiness. L of delta of t minus pi is nothing but e raised to minus pi s. Instead of a, we have pi here. Apply Laplace transforms on both sides. And here we have L of y double dash is equal to s square into capital Y of s minus s into y of 0 minus y dash of 0. L of y dash is equal to s into y dash minus y of 0. L of y is equal to capital Y of s. And then substitute for y of 0, y dash of 0. Then make everything of y of s together. Make them together and form the braces. And then find what is y of s. So in the end, what we are getting as y of s is equal to e raised to minus pi s plus 2 divided by s square plus 2s plus 2. Okay, so we are for finding it out and splitting, and for the our easiness, we are splitting them out as e raised to minus pi s divided by this function, this term, plus s plus 2 into this function. So we had already seen when this kind of function comes, actually this will arise into the roots being complex. So this can be written as s square plus 2s plus 2 is very close to s plus 1 the whole square plus 1. So we are substituting instead of s square plus 2s plus 1, we are replacing by s plus 1 the whole square plus 1 square. Okay, and here what we are doing is we have an s plus 1 here. So if we have an s plus 1 from here, there will be some kind of use plus 1. Okay, then we again split that 1 divided by s plus 1 the whole square plus 1 square. So this is the finalized easier version of y of s, so that we can find the L inverse. Okay, so this y of t is equal to L inverse of y of s. So that is equal to L inverse of e raised to minus pi s into 1 by s plus 1 the whole square plus 1 square plus s plus 1 divided by s plus 1 the whole square plus 1 square plus 1 by s plus 1 the whole square plus 1 square. So here what we are keeping this as such. Okay, everything as the same. We are splitting them by using the linearity property. Okay, we have L inverse of s by s square plus 1 is equal to cos t. L inverse of 1 by s square plus 1 square is equal to sin t. So by first shifting theorem or inverse Laplace transforms, L inverse of s plus 1 divided by s plus 1 the whole square plus 1 square can be written as equal to e raised to minus t into cos t. And similarly, L inverse of 1 by s plus 1 the whole square plus 1 square is equal to e raised to minus t into sin t. Okay. And suppose if we have to find L inverse of e raised to minus pi s into this quantity. So that becomes the second shifting theorem, the corollary of the second shifting theorem. And here instead of a, we are having pi. So here we'll be having u of t minus pi into f of t minus pi, where this f of t comes from the Laplace inverse of the value sitting here. Okay. So small f of t is equal to L inverse of 1 by s plus 1 the whole square plus 1 square, which is equal to e raised to minus t into sin t. Then f of t minus pi is equal to e raised to minus of t minus pi into sin t minus pi. Okay, so you are substituting what we got here, e raised to minus t minus pi into sin t minus pi into here. Okay, so you are getting the three terms. So combining together, you get y of t is equal to y of t is equal to u of t minus pi into e raised to minus t minus pi sin t minus pi plus e raised to minus t into cos t plus e raised to minus t into sin t. So that is the answer. And what you have to do the next is solve these assignments, and it is mandatory for you to solve these assignments, because unless you are solving by yourself, it will become very difficult for you to solve the problems when it comes to the examinations. So do solve these problems, and definitely I'll be giving assignments in the Google Classroom so that you can submit those assignments after you try them out. So, thank you for the session, and we'll see very soon.